NASA just confirmed. Water is erupting from Enceladus. There is a moon out at Saturn that is only 504 kilometers wide. You could drive across it in a day, if it had roads. It is smaller than the state of Arizona. It is frozen solid. Its surface sits at around -200 degrees Celsius, and it is the most reflective object in the entire solar system. And it is spraying a jet of liquid water into space that reaches roughly 10,000 kilometers. Not 10,000 meters, 10,000 kilometers. That is a plume about 20 times wider than the moon producing it. Picture a golf ball throwing a stream of water the length of a football field, and the golf ball never runs out. And nobody expected Enceladus to be doing anything like this. Stick around, because I am about to walk you through what scientists actually just confirmed about that plume, what is inside it, and why it changed the short list of places we look for life. And hit subscribe now, because this channel breaks down real space discoveries without the exaggeration. Let's go back to where this story actually begins. In the summer of 1789, in a garden in Slough, England, a 50-year-old man was standing under a telescope he had built himself. His name was William Herschel. He was not a professional astronomer, because that job barely existed yet. He was a musician, an organist. He composed symphonies for a living and ground his own telescope mirrors in his spare time, mixing the metal alloy by hand and polishing it for hours until his arms gave out. The telescope above him was 40 feet long. It was the largest in the world. It was also, by his own account, an awkward and frustrating machine that took a crew of people to aim. On the 28th of August, 1789, he pointed it at Saturn. He saw a faint point of light close to the rings. Then another. 2 new moons, in a matter of weeks. The smaller and more difficult of the two was a dim speck that only showed itself when the rings were edge-on and their glare was reduced. Herschel logged it and moved on. He did not name it. His son John did that, decades later, in 1847, calling it Enceladus, after one of the giants of Greek myth. For the next 190 years, that is essentially all Enceladus was. A dot, a line in a table, a number in an orbital catalog. And there was a good reason for that. Enceladus is small, and it is parked next to one of the brightest, most visually overwhelming objects in the sky. Saturn's rings scatter light everywhere. A faint moon close in gets washed out. Through most of the 19th and 20th centuries, the best telescopes on Earth could confirm that Enceladus existed and could track where it was, and that was the end of the list. No surface features, no composition, no temperature. It was also, on paper, the least interesting kind of object in the solar system. Small bodies lose their internal heat quickly. Heat escapes through the surface, and small bodies have a lot of surface relative to their volume. Every textbook model said that a moon this size, this far from the sun, formed billions of years ago, should be frozen through to the center and geologically dead. No volcanism, no motion, nothing happening. That expectation was so firmly held that when the first evidence arrived, the instinct was to look for an error in the instrument. Voyager 1 and Voyager 2 flew through the Saturn system in 1980 and 1981. Voyager 2 got the better look. It sent back images of a small moon with a surface that was startlingly bright and startlingly smooth in places. No craters in some regions. That was strange. Craters accumulate. A surface with no craters is a surface that has been resurfaced recently, geologically speaking, and small icy moons are not supposed to have the energy to resurface anything. Voyager also noticed something else. Saturn has a very faint outer ring, called the E ring. It is broad and diffuse, and made of tiny ice particles, and it was densest exactly where Enceladus orbits. Nobody could explain that. The dots did not get connected. Voyager kept moving, because that is what Voyager did. The turning point came 24 years later. Cassini-Huygens launched on the 15th of October, 1997. It took nearly 7 years to get there, and entered orbit around Saturn on the 1st of July 2004. It was a large spacecraft with a large instrument list, and among those instruments was a magnetometer, which measures magnetic fields. In early 2005, Cassini made distant passes by Enceladus, and the magnetometer team saw something they did not like. Saturn's magnetic field was being bent around the little moon. Field lines drape like that when they run into an atmosphere, or into charged particles. A dead ball of ice should not have either. The magnetometer lead, Mikhail Doherty of Imperial College London, pushed for something that mission planners hate. She wanted the flight plan changed. She wanted Cassini to go closer. Changing a flyby altitude on a billion-dollar spacecraft, in a system full of ring debris, on the strength of a magnetic wobble, is not a small ask. She got it approved anyway. On the 14th of July 2005, Cassini passed about 168 kilometers above the south pole of Enceladus. And there it was. Here is the chain of physics, one step at a time. Enceladus does not orbit Saturn in a perfect circle. Its orbit is slightly stretched, and it completes one lap in about 33 hours. 33 hours. Hold on to that number. Because the orbit is stretched, the distance to Saturn changes constantly over those 33 hours. And Saturn is enormous. So the gravitational pull on the near side of Enceladus is measurably stronger than the pull on the far side, and that difference rises and falls with every orbit. That squeezes the moon, then releases it, then squeezes it again, every 33 hours, forever. The orbit stays stretched because of another moon, Dione, further out. Enceladus completes exactly 2 orbits for every one that Dione completes. That is called an orbital resonance, and it means the 2 moons line up in the same configuration over and over, tugging on each other in the same direction each time. That repeated tug keeps the orbit from relaxing into a circle. Without it, the squeezing would have stopped long ago. Squeezing something flexes it. Flexing something heats it. This is not exotic physics. Bend a paperclip back and forth and the bend gets warm. It is the same principle, scaled up to a body 504 kilometers across. That heat does not simply vanish. It builds up in the interior, and under an ice shell, it has nowhere to radiate. So it melts ice from the inside. Beneath the crust of Enceladus, there is liquid water, not a pocket, not a lake. Measurements of the moon's slight wobble as it orbits, published by Cassini scientists in 2015 and 2016, only make sense if the entire ice shell is disconnected from the rocky core. The wobble is too large for a solid body. That means a global ocean, wrapped around the whole moon, under an ice shell averaging perhaps 20 kilometers thick. At the South Pole, that shell is much thinner, and it is cracked. 4 long parallel fractures run across the southern terrain. Cassini's imaging team named them Alexandria, Cairo, Baghdad, and Damascus, and everyone else calls them the Tiger Stripes. Each one is roughly 130 kilometers long, about 2 kilometers wide, and around 500 meters deep. Those cracks connect the ocean to space, and they are not 4 neat pipes. When Cassini imaged the South Pole with the sun behind the moon, backlighting the region, the plume resolved into something closer to a curtain. Dozens of individual jets distributed along the length of the fractures, some brighter than others, all leaning outward and merging into a single haze further up. The imaging team eventually cataloged around 100 discrete sources. The other detail worth stating is the temperature contrast. The general surface of Enceladus sits near -200 degrees Celsius. Along the Tiger Stripes, Cassini's infrared instrument measured material substantially warmer than the surrounding terrain. Not warm by any human standard. Warmer than it has any business being, on a moon that should have gone cold billions of years ago. Those warm stripes are the exhaust ports. Everything the ocean is made of comes out through them. Now, the last step of the chain. And space, at that distance, is a vacuum. Liquid water in a vacuum cannot stay liquid. It flashes. Part of it turns instantly to vapor, and part of it freezes instantly into ice grains. And the vapor expansion drives the whole mixture out through the crack, at high speed. Which is why a frozen moon smaller than Arizona is currently venting a plume that reaches 10,000 kilometers into the dark. Now understand what it took to measure that. Saturn is not nearby. Depending on where Earth and Saturn are in their orbits, the distance ranges from roughly 1.2 to 1.6 billion kilometers. A radio signal, moving at the speed of light, takes somewhere between about 68 and 92 minutes to cross that gap in one direction. So there is no such thing as flying Cassini in real time. Every command was written, tested, uploaded, and then executed hours later by a machine that was entirely on its own. If something went wrong during a flyby, the team on Earth would not learn about it for over an hour, and by then the flyby was long finished. There were no repairs. There was no second attempt at a given pass. There was no spare Cassini, and the thing they wanted to fly through was a jet of ice grains. hitting the spacecraft at relative speeds of several kilometers per second. At that speed, a grain of ice is not a snowflake. It is a projectile. Flying a spacecraft deliberately into the plume meant accepting that the instruments would be sandblasted and that the ice grains would shatter on impact rather than arrive intact, which complicates every measurement you try to make from them. They did it anyway, repeatedly, and there was a harder constraint underneath the physical one. Cassini was designed and built before anybody knew Enceladus had a plume. The instrument list was locked in the early 1990s. The mass spectrometer aboard was built to sample Titan's atmosphere and Saturn's magnetosphere. It was never designed to characterize the chemistry of an alien ocean, because when it was designed, nobody thought there was one. So every result you are about to hear was obtained with the wrong tool, used well. That is worth holding on to, because it explains both how much Cassini found and why it could not finish the job. There was also a fuel limit. Cassini carried a finite amount of propellant, and every flyby of every moon spent some of it. The Enceladus passes competed directly with Titan science, with ring science, with everything else the mission had promised to deliver. Each dive through the plume was a decision to not do something else, made by people who knew the spacecraft would never be replaced. The deepest of those passes came on the 28th of October 2015. Cassini dropped to about 49 kilometers above the surface and flew straight through the densest part of the plume. 49 kilometers. That is lower than most weather balloons get above Earth. And the reason it had to be that low is simple. The instruments could only sample what physically hit them. To read the chemistry of an ocean, they had to put the spacecraft inside the spray. Think about the actual sequence there. A machine launched in 1997, designed in the early 1990s, using computing hardware that a modern phone would embarrass, was threaded through a jet of ice at a moon nobody knew was active when the mission was designed, more than 1 billion kilometers from anyone who could help it. The first thing Cassini found in the plume was salt. The ice grains were not pure water ice. Many of them carried sodium and potassium salts, in proportions that look like water that has been sitting in contact with rock. That is the whole point. Fresh water does not have that chemistry. Ocean water on Earth is salty because rivers have spent hundreds of millions of years dissolving minerals out of rock and carrying them to the sea. Salt in the Enceladus plume means the water down there is touching the rocky core, not just sitting in a sealed pocket of melted ice. Then came something smaller and stranger. Cassini's dust analyzer picked up nanometer-scale grains of silica. Silica is essentially the mineral that makes up sand and quartz. Grains that small, of that composition, form under a narrow set of conditions. And laboratory work, published in 2015 by a team led by Xiangwen Xu, concluded those conditions require water in contact with rock at temperatures of at least around 90 degrees Celsius. So, there is hot water down there. Not lukewarm, hot water, on the sea floor of a moon whose surface sits near -200. On Earth, we have a name for hot water rising through rock on a seafloor: hydrothermal vents. And on Earth, hydrothermal vents host entire ecosystems that never see sunlight and do not care that it exists. What remains unexplained is the size and stability of that system. Nobody has directly imaged the seafloor of Enceladus. Nobody knows how many vents there are, how long any one of them lasts, or whether the whole arrangement has been running for 100 million years or turned on relatively recently. The 33-hour squeeze provides the energy. The distribution of that energy inside the moon is still modeled, not measured. In April 2017, a team led by Hunter Waite at the Southwest Research Institute published a result in the journal Science that changed the conversation. Cassini's mass spectrometer had detected molecular hydrogen in the plume, a lot of it, relative to what anyone expected. Here is why that matters, in plain language. Hydrogen is a fuel. Specifically, it is the fuel used by some of the oldest and simplest metabolisms we know of on Earth, in a process called methanogenesis. Certain microbes combine hydrogen with carbon dioxide, extract energy, and release methane as waste. They need no sunlight. They need no oxygen. They need hydrogen, carbon dioxide, liquid water, and a bit of warmth. Cassini detected hydrogen. Cassini detected carbon dioxide. The water was already confirmed, and the silica said the water was hot. That is a complete energy source, not evidence of life. An energy source that life, if it were there, could live on. And the reason the hydrogen abundance was so striking is that hydrogen is light and it escapes easily. Finding a lot of it means it is being produced continuously. most plausibly by hot water reacting with rock on the ocean floor. A stock of hydrogen sitting around from the moon's formation would have leaked away long ago. The honest limit of this finding is important, and the researchers said it clearly at the time. Hydrogen being present means nothing is eating it. That could mean there is nothing there to eat it. A biosphere would consume the hydrogen and lower its abundance. So this result tells you the pantry is stocked. It does not tell you anyone is home. In June 2018, a team led by Frank Postberg published a result in Nature that came from the same Cassini instrument. Inside individual ice grains from the plume, they had found complex organic molecules. Not simple methane. Large carbon-bearing macromolecules, with masses above 200 atomic mass units, containing rings and chains of carbon. Organic does not mean biological. Complex carbon chemistry occurs without life, and it is common in comets and in the interstellar medium. But complex organics are the raw material of biology, and finding them dissolved in an ocean rather than frozen into a comet is a different situation entirely. Then, in June 2023, the same broad research group published something they had been hunting for years: phosphates. In the ice grains of Enceladus, in concentrations that laboratory comparisons suggested were far higher than in Earth's own oceans. Phosphorus is one of the 6 elements considered essential to life as we know it. It is in DNA, it is in RNA, it is in the cell membrane, it is in ATP, the molecule your body uses to move energy around, right now, in every cell you have. And phosphorus is the one that is usually missing. It is comparatively rare, it locks itself into minerals easily, and its scarcity is a standing problem in origin of life chemistry here on Earth. So take the full inventory that a spacecraft designed in the early 1990s pulled out of a spray of ice at a moon 504 kilometers wide, over 1 billion kilometers from Earth. Liquid water, global, salty, in contact with rock, hot at the base, carbon dioxide, molecular hydrogen, complex organic molecules, ammonia and phosphorus, every ingredient on the list, all of it, venting into space for free, through cracks in the ice, where a passing spacecraft can simply fly through and read it. There is no other place we know of that does this. Cassini's mission ended on the 15th of September, 2017. It was deliberately flown into Saturn's atmosphere and destroyed, specifically so that it could never fall onto Enceladus and contaminate it. That decision was made because of what Cassini had found there. After that, we had no spacecraft at Saturn. The measurements stopped. Then, in late 2022, the James Webb Space Telescope was pointed at the Saturn system, and its near-infrared spectrograph looked at Enceladus. The results, led by Geronimo Villanueva at NASA's Goddard Space Flight Center, were published in Nature Astronomy in 2023. Webb was not sitting inside the plume. Webb was roughly 1.4 billion kilometers away, at a gravitational balance point out past the moon's orbit, doing this remotely, and it saw the plume extend approximately 10,000 kilometers from the moon. Sit with the proportions of that. The moon is 504 kilometers across. The plume is about 20 times that length. If Enceladus were a basketball, the water jet would reach across a tennis court. Webb also measured the output rate. Roughly 300 kilograms of water vapor per second. Translate that. 300 kilograms a second would fill an Olympic swimming pool in about 2 hours, continuously, from a frozen object smaller than Arizona, with no external power source other than the 33-hour squeeze from Saturn's gravity. And here is the part that contradicted expectations most directly. Webb's data indicated that only a fraction of that water, in the region of 30%, stays in a donut-shaped torus along the moon's own orbital track. The rest disperses outward and feeds the wider Saturn system. There is one more thing about the Webb result that deserves emphasis, and it is about method rather than about Enceladus. Webb did not need to go there. It resolved a plume of water vapor from a moon 504 kilometers wide, across roughly 1.4 billion kilometers of empty space, by reading the specific wavelengths of infrared light that water absorbs and emits. It measured the shape of the plume and the rate of the outflow from a fixed position near Earth. That is a capability we did not have a decade ago, and it applies to more than Saturn. If a small icy body somewhere else is venting water, we now have a way to notice it, without spending 7 years flying a spacecraft out to check. The same instrument, pointed at the right targets, is the fastest survey tool we have for finding the next Enceladus. One 504-kilometer moon is supplying water to a planetary system. It is the source of Saturn's E-ring, which was the anomaly Voyager saw in 1981 and could not explain. Water from that ocean has been detected in Saturn's upper atmosphere. A single small moon is quietly plumbing an entire region of the solar system, and it has presumably been doing it for a very long time. What researchers still cannot fully explain is the plume's variability. The output is not constant. It changes over the 33-hour orbit, apparently as the tiger stripes are squeezed shut and pulled open by the same tidal cycle that heats the interior. But the timing does not match the simplest models cleanly, and the long-term behavior, over years and centuries, remains close to impossible to constrain from the handful of observation windows we have. There is one more mismatch worth stating plainly, because it is the kind of thing that gets left out of headlines. Measurements of the heat coming out of the South Polar region put the output in the range of several gigawatts. Published estimates from Cassini's infrared instrument have run as high as around 15 gigawatts, though the number is debated and depends heavily on how you separate the moon's own heat from reflected sunlight. Standard tidal heating models, assuming the moon is in a long-term equilibrium, predicted roughly 1 gigawatt. The moon is losing more heat than the simple models say it should be able to generate. There are candidate explanations. The rocky core may be porous and fractured, letting water circulate through it and extract heat far more efficiently than a solid core would. The moon may not be in equilibrium at all, and we may be watching an unusually active phase that will not last. The internal structure may simply be more complicated than the models assume. Nobody has resolved it. It is one of the cleanest open problems in planetary science, and it sits underneath everything else in this story, because the energy budget determines how long that ocean has been liquid, and how long the ocean has been liquid determines whether there has been time for anything interesting to happen in it. 4 billion years is a long time for chemistry to run. 50 million years is not. Right now, we cannot tell you which one it is. And there is a version of this that is genuinely uncomfortable for the models. If the current output cannot be sustained indefinitely, then we are looking at a burst, which would mean that out of 4.5 billion years of solar system history, we arrived, built telescopes, launched a spacecraft, and pointed it at the right moon during the exact window when it happened to be spraying. That is either a remarkable coincidence, or the models are missing a mechanism that keeps this running far longer than the simple math allows. Most researchers lean toward the second option, because the first requires too much luck. But leaning is not knowing. It is an open question, and it will stay open until something goes back and measures the interior directly. So the obvious question: if the plume is right there, and it carries material straight out of the ocean, and we have already flown through it, why do we not know whether anything is alive down there? Because detecting life is a much harder measurement than detecting chemistry. Cassini could tell you which molecules were present and roughly how much of each. It could not tell you the shape of those molecules or how they were arranged, and that arrangement is where the evidence actually lives. Biology leaves fingerprints in patterns, not in single ingredients. It prefers certain amino acids over their mirror images. It builds fatty acid chains at particular lengths and skips others. It shifts the ratio of carbon isotopes because living cells find the lighter isotope easier to process. Those are the signals worth looking for, and reading any of them requires instruments Cassini did not carry. There is a second problem, and it is a mechanical one. Ice grains hitting a spacecraft at several kilometers per second do not survive intact. They shatter. Fragile molecules break on impact, and what the instrument records is the wreckage, not the original. That is one reason the 2018 organics result was framed carefully. The team knew they were reading pieces. A mission built for the actual question would need to do 3 things Cassini could not: fly slowly through the plume so grains arrive whole, carry instruments designed from the start to measure chirality, chain length distribution, and isotope ratios, and collect enough material over enough passes that a positive result cannot be dismissed as contamination from the spacecraft itself. None of that is science fiction. All of it is engineering that we know how to do. It has simply not been funded, launched, and flown. Which means the honest status of Enceladus in 2026 is this: we know the ocean is there. We know it is salty, warm at the base, and stocked with every element and energy source we consider necessary. We know it is venting 300 kilograms of itself into space every second through cracks in a 504-kilometer moon. and we do not know, and currently cannot know, whether anything in it is alive. So what happens next? There is no spacecraft at Saturn today, and there will not be one for a long time. That is the plain reality of it. The 2023 Planetary Science Decadal Survey in the United States, which sets flagship mission priorities, ranked an Enceladus mission concept as one of its highest priorities, behind only a mission to Uranus. The concept, called Enceladus Orbilander, would orbit the Moon, sample the plume repeatedly, with instruments designed from the start to look for biosignatures, and then land on the surface to collect fallen plume material directly. The European Space Agency has also identified the icy moons of the outer planets, with Enceladus specifically named, as the theme for a future large-class mission. Neither is built, neither is funded to completion. Realistic launch windows for a mission of that class fall in the 2030s at the earliest, with cruise times to Saturn of roughly 7 years or more, meaning the data that could actually answer the question would arrive, at best, in the 2040s, more likely later. That is not pessimism. That is orbital mechanics and budget cycles, and both are indifferent to how badly anyone wants the answer. But Enceladus does not wait for us. Right now, while you are watching this, the Moon is being squeezed on its 33-hour cycle. The cracks are opening. 300 kilograms of water per second is going out through the tiger stripes and into vacuum. The plume is reaching 10,000 kilometers. It was doing that when Herschel found the dot in 1789. It was doing it when Voyager flew past and did not understand the E-ring. It will be doing it whether or not anyone ever builds the spacecraft to go and read it properly. So what does all of this actually add up to? A moon 504 kilometers wide. A global ocean under 20 kilometers of ice. A 33-hour squeeze that keeps it liquid. A plume reaching 10,000 kilometers, carrying salt, hydrogen, organics, and phosphorus into open space, at 300 kilograms every second. Every ingredient we know life needs, in one place, sprayed outward, where a passing spacecraft can simply fly through it and take a reading. We have not found life at Enceladus. Nobody has claimed we have, and this channel is not going to be the one to start. What we have found is a small frozen moon that we wrote off for 190 years, which turned out to be running the most accessible habitable zone chemistry in the solar system, and which we noticed almost by accident, because one scientist argued for a course correction. There are dozens of icy moons out there we have never looked at closely. It is genuinely worth wondering what those might be hiding too. If you want more of this, subscribe and turn on notifications. Everything here is grounded in real published research rather than exaggerated headlines.